Welcome to the manufacturing process lecture. Today we are going to cover water jet and abrasive water jet machining. This is lecture number 37, belongs to module number 9, which is non-traditional manufacturing. I am Dr. Soumitra Pal from Department of Mechanical Engineering, IIT Kharagpur. Now let us go into the instructional objectives. After going through these lectures, you will be able to list different non-conventional machining processes. Already we have covered some of them. If you remember the previous lecture and the lecture before that, we would be able to differentiate between water and abrasive water jet machining. You would be able to list different things. What are they? You would be able to list different water jet and abrasive water jet systems. You would be able to list what are the different modules within abrasive water jet systems, list their applications, list their advantages, and what are the materials that can be processed by abrasive water jet machining process. Not only that, you will be able to describe the functions of different elements or modules which are required to build a abrasive water jet system, describe the mechanism of material removal process, develop models for mechanism of material removal, identify parameters related to product quality. Whenever we undertake any manufacturing process, we are basically developing a product. So, product quality is very, very important. So, you would be able to identify what are those product qualities and how the other abrasive water jet parameters affect them. You would be able to identify limitations of abrasive water jet machining. Any manufacturing process would have their advantages as well as limitations. So, knowing the limitations are also very important. Moreover, the futuristic direction of R&D in the area of abrasive water jet machining would also become clear once we cover this particular lecture. Now, in non-traditional machining, the different processes can be grouped into different groups depending on what is the energy source. Already in the last lecture or the previous lecture before that, we have identified them. One such group is mechanical processes, one is thermal processes, electrochemical processes and chemical processes. Say for example, you may have heard about electro discharge machining, laser beam machining. They are the basic energy source which is relevant for mechanism of material removal is thermal process. So, it is listed under that. Today we are going to cover, as I said, water jet and abrasive water jet. There the energy source is mechanical. Similar processes under mechanical process are ultrasonic machining and abrasive jet machining. Today we will be concentrating, as I said earlier, on water jet and abrasive water jet machining. Now, what is abrasive water jet or water jet machining? In both of them, we require very high pressure water. So, we require high pressure water. So, this is the pipe which carries the high pressure water. How high would be the pressure? The pressure of the water would be as high as 4000 bar. Now, you may question me, how much is 4000 bar? Typically, in a 3-storied building, if you have an overhead tank, then in the ground floor you will get a pressure of around 1 bar. So, 4000 bar is a lot of pressure. If you convert that into the stress unit, general stress unit, 4000 bar is around 400 MPa. Most of the alloy carbon steels shear strength would be less than 4000 MPa. So, high pressure at 4000 bar is rather very, very high. Then what is done with the high pressure water? High pressure water is allowed to come out of a small orifice. How small is this orifice? This orifice is really small, it is around 0.1 to 0.3 millimeter. So, the pressure energy of the water of 4000 bar gets converted into the potential energy. So, once the water comes out of the orifice, the water jet is formed. So, water jet is available here. What is the velocity of this water jet? If you use Bernoulli's equation, where we will be going into in detail at a later stage, this velocity can be calculated as 1000 meter per second, that means 1 kilometer per second. So, if you have to move from Kharagpur to Calcutta, which is 120 kilometers at this particular speed, it will take only 2 minutes. So, that is the nature of velocity that comes out in water and abrasive water jet machining. Now, water jet machining can be divided into two groups. One is water, pure water jet, another one is water jet with stabilizer. In pure water jet, this part of the schematic is not relevant. Water comes out and directly machines my job. This is my job, it directly machines it. How it machines? All of us, we have seen waterfalls. Just below the waterfall, there is erosion of the granite or the rock. So, such low pressure water can also erode materials. So, this water can also machine jobs. However, it cannot machine metallic alloys, it can machine polymers, it can machine leather and stuff like that. The cutting ability of this water jet can be enhanced by adding abrasives through this particular pipe. So, this abrasive mixes with the water, comes out, and this can also machine the job. Once again, let us come back to the pure water jet and with stabilizer. Pure water jet means it is commercially pure water. When it comes out, it flares out. When it flares out, because of entrainment of air from the atmosphere, as it flares out, its cutting ability, its amount of material it can cut definitely reduces. So, we have to somehow control this flare. How do we control this flare? We add stabilizer. What are these stabilizers? These stabilizers are nothing but long chain polymers having higher molecular weight. So, once we add those stabilizers with the water jet, the flare reduces, it becomes much more focused, and we can use the total power of water jet for machining. This is about water jet. The other part of the story is abrasive water jet. There are two different systems of abrasive water jet. One is called entrained abrasive water jet system and another one is called suspended abrasive water jet system. Out of these two systems, entrained abrasive water jet is much more popular and widely used in the industry. Suspended water jet system is also used, however, its penetration in the manufacturing market is not too high. In entrained water jet, it basically is composed of three phases: abrasive, water and air. In suspended, it is composed of abrasive and water. Once again, we will go later on into different variants of suspended water jet. Now, what are the general experimental conditions? So, what is this? This is a device, I have not yet named the device, which issues high pressure abrasive water jet. This is called the cutting head. How it issues? I have explained briefly. Now, there is an orifice which basically transfers the pressure energy of the water into kinetic energy of the water or generates the water jet. This orifice is made up of sapphire. Its diameter is around 0.1 to 0.3 millimeter. So, it is submillimetric. In that, the high pressure water is generated. After that, we have a mixing chamber. We will describe this one in future slides, and you have a focusing tube. Within the focusing tube, the abrasives are added. So, this is my focusing tube. The inner diameter of the focusing tube is around 0.8 to 2.4 millimeter. We have already discussed what kind of pressure we are using. The pressure of water is around 2500 to 4000 bar, which is 250 to 400 MPa if you are conversant with that unit. Now, what are the abrasives which are added here? Abrasives are nothing but silicon oxide or sand. Typically, they are called garnet or olivine. Then whenever we are specifying the material, we need to specify the size as well. These are the size of abrasive which is used. This is mesh size 125 and this is mesh size 160. You have already come across, you have gone through the grinding lecture. So, you know how much, what do you mean by 120 mesh and what do you mean by 60 mesh. Now abrasives are being fed, so I need to meter how much abrasing is being fed. Generally abrasive flow rate is around 0.1, that is 100 grams to 1 kilogram per minute. Standoff distance. What is standoff distance? Any jet cutting process has a standoff distance. This is the end of my focusing tube and this is my job. So this particular distance is my standoff distance, and that standoff distance is generally 1 to 2 millimeter. You may ask me, can I not have a standoff distance of 25 millimeter? Yes, you may have, but when you have a standoff distance of 25 millimeter, you are going to waste your energy of the abrasive jet. The standoff distance should be that much so that there is no interference between the focusing tube and your material that you are processing, but it should not be unnecessarily large. Typically in the industry, standoff distance of 1 to 2 millimeter is used. Next comes the question of impact angle. This is my impact angle, that is the angle between my jet and the job. In this particular diagram, the impact angle has been shown as 90 degree. It could have been inclined as well. So inclined impact angle is typically kept at 60 degree to 90 degree. Now what is the reason for inclining the jet? If I need a cut along this particular direction, then only I will incline the jet, or else typically my inclination angle or impact angle would be 90 degree. Now traverse speed. If my jet is being issued like this, I would machine it in this direction. If the jet is stationary, I would only get a hole. I am not interested in getting a hole. I need to machine it, I need to slit it, slot it. So I have to give a velocity either to the jet or to my job. So that is called the traverse velocity or traverse speed. Typically in abrasive water jet machining, it is around 100 meter to 5 meter per minute, 100 millimeter per minute to 5 meter per minute. Now how much is the depth of penetration? So what is this distance which is generally achieved in abrasive water jet machining? It can be as low as 1 millimeter, it can be as high as 250 millimeter. 250 millimeter in actual domain would be at least this much. So this is around 250 millimeter. So this is this long, it is rather long. Now let us go into how the system looks like. This is my photographic view of the abrasive water jet system. This is my cutting head, the schematic of which you have seen already here. So this is the same thing, it is the photographic view. So through this the high pressure water is coming, abrasive is added from this portion and abrasive water jet is coming out here, and the yellowish substance that you can see is the job covered with water and abrasive. The whole this is nothing but the zoom view of this particular portion. So cutting edge is this small. Below that you have your workpiece. This could be your workpiece which you need to cut possibly along a complex contour. So you need a CNC system. So this is the CNC system and this is the CNC table where the job is maneuvered to get a particular contour. Any contour you want under the CNC control that you can get. Now before going into the process description, let us go into advantages of abrasive water jet machining process. Compared to conventional machining processes as well as compared to non-traditional machining processes, its setup is extremely fast, and as because most of the time a CNC is done, you can always do the CNC programming. So it is not going towards a hard automation, but it is a soft automation. You can even use it for batch production. There is no need that it has to be used under mass production situation. Very little fixturing is required, as because most of the time fixturing is almost non-existent. It is a very good process technology which can be adapted for batch production scenario. It can virtually machine any 2D shape on any material. How can it machine any 2D shape? Because most of the time abrasive water jet system would be having a CNC table along with it, and because of its inherent properties it can almost machine any material. We will come to that list after some time. It has very low side force. When it is machining an object, there is almost no side force. So you require very less amount of work holding device. So it can be implemented very fast. Another great advantage of abrasive water jet system compared to other jet cutting processes like plasma arc machining or laser beam machining is that, which is the last point. almost no heat generated on your part, there is no thermal damage to the part. Even if your part is sensitive to heat, it can be machined. If it is made of plastic, you can machine it. If it is made of glass fiber, you can machine it. There is absolutely no heat affected or thermal damage as compared to plasma arc machining or laser beam machining, which is also a beam or jet process. Now, we were always saying that it can machine any material. You go through this list, you will be convinced. Now, here they are in two different colors for a particular reason. Abrasive water jet machining, that is AWJM, can machine steel, it can machine aluminum, name any non-ferrous material it can machine, super alloys, titanium super alloys, nickel alloys, it can machine, polymers it can machine. So, it can not only machine so called high strength alloys, it can also machine polymers, honeycombs. They are very difficult to machine because the whole system distorts, but they can be machined. Metal matrix composites and ceramic matrix composite, these are newer development, these have been developed possibly in last 10-20 years, they can be very efficiently machined. Now, the other end of the spectrum is water jet machining. Water jet machine cannot be used for machining this, abrasive water jet machine is required. Then what for am I going to use water jet? It can be machined for reinforced plastic, it can machine wood, it can also to some extent machine, say for example leather and other kind of material. Abrasive water jet machine can machine concrete, metal polymer laminate, glass fiber laminate. These two materials are very important materials for aerospace applications, and they can be very efficiently machined by abrasive water jet machining. Water jet can machine wood, reinforced plastics, leathers. So, in our leather industry, they do have lot of application. As they can machine wood in our furniture industry, water jet does have lot of application. Now, what are the applications? Once again, they are in two different colors. So, water jet can be used for cutting soft material, only water jet, not abrasive water jet. Cutting frozen meat, this may not be a very relevant application for our country, but otherwise it is an application. It can be used for machining textiles, it can be used in leather industry, it can be used for paint removal. However, for paint removal you do not require 4000 bar, you do not require such a high pressure, you require around 200 to 500 bar, or else instead of removing the paint, it will remove the material itself. It can be used for cleaning. Now, there is another very important application of high pressure water jet or high pressure jet. It can be used for mass immunization, it can also be used for surgery. I am not going into this because this domain is beyond the manufacturing. Now, abrasive water jet machining can be used for pinning, for introducing compressive residual stresses. It can be used for cutting, it can be used for pocket milling, drilling, it can even be used for turning. Another very strategic application of abrasive water jet machining is nuclear power dismantling. Now, let us have a look at actual parts which have been machined by abrasive water jet. So, these are few parts which I have selected. Now, as you can see, this is a very slender part having a less thickness and the length is rather high, and there is intricate design. So, abrasive water jet machine has machined this with such a good precision that that intricate design has been kept. This one is a standard part with some holes. These holes are typically of around 3 to 4 millimeter diameter. So, abrasive water jet has machined it like this by trepanning operation. There is a circular part as well. So, this has been done using the circular interpolation. So, this is from CNC part point of view is a rather complex part which can be machined using abrasive water jet. These two parts shows what is the precision or the accuracy that you can achieve using abrasive water jet. This is basically a disc where some grooves have been cut, and this one shows the same thing when it has been opened up. Okay, you can see what is the level of precision that can be achieved with abrasive water jet machining. This one basically shows this particular surface which I am hatching, this is not vertical, this is slant. So, abrasive water jet, as I said earlier, can be inclined, it can be made inclined by 60 degree up to 60 degree, so that you can get an inclined surface. Okay. Now we are gradually going into the composition of the abrasive water jet system. As I said earlier, that we will be mainly restricting ourselves to the entrant system, because that is the most popular system. Now there are three parts here. This is one part, this is the other part, and this is the other part. This particular list basically generates the high pressure water. So you have a low pressure booster pump, hydraulic unit, additive mixture. This hydraulic unit drives the intensifier. You require an accumulator, I will explain. Then you require a flexible line which can carry water at 4000 bar. That water is brought to this particular unit. This is called the cutting head. This is called the cutting head. It is composed of on-off valve, which basically allows the water to come out of orifice or not to come. You have a mixing chamber and focusing tube, which basically focuses the water and abrasive together. Once the water is available, it has already machined the job, still it does have lot of energy. If you put your hand behind it, your fingers will be cut off. So you require a system which catches the water, that is the catcher. As I said initially, you require a CNC table, and as because you are adding abrasive, you also need a abrasive metering device. So these are the different modules which I have described. Gradually we will go into pictorial description of them. So this part which I have discussed in the previous slide is here, and that is the pictorial description. So what are the things here? This is my number 1 LP booster pump, low pressure booster pump. This water is the plant water, whatever water is available in your organization or plant. This is possibly at 1 to 10 bar depending on your municipal supply. This pressure is boosted using this LP booster pump. To what value? This is typically boosted to around 100 bar. Then if required, you can add additives. Why additives are added? To remind you once again, so that my water does not flare up. This water goes into this part. This is the intensifier. Now intensifier is driven by hydraulic drive. This is my hydraulic drive. What is this for? This is the direction control valve. At one time it allows water to enter through this port, in another time it allows the water to enter through this port. If it is water is entering through this port, it creates some pressure, so the cylinder goes in this direction, and as because there is a area difference, I get a huge pressure of water at this particular port, which is 4000 bar. Now this 5A is my low pressure intensifier, which is this part. 5B is the high pressure intensifier, which is this part. 6 is accumulator, this one. Now whenever this intensifier is reciprocating, what happens? At this, whenever it reciprocates, the velocity becomes 0, so there is a pressure drop. So accumulator accumulates the water. It's something like a flywheel, okay, so that the energy becomes available all the time. Once from the accumulator, it comes out through this. This is entry to the cutting head. So this is my schematic description of the flexible tube which can carry water at such a high pressure. Now this slide explains the action of the intensifier in a better manner. So what do I have here? This pH, where from is it coming? It is coming from the hydraulic drive. What is this pH? This pH is 100 bar. Let us assume for this moment that there is the direction control valve, and this direction control valve is currently allowing water to enter this particular chamber. So what happens? The piston starts moving in this direction. So this one also start moving in this direction. From the force balance, very easily you can see the water which will be coming out of this, that pressure would be much higher. Why it would be higher? Because this area AHP is much less than this area, which is ALP. Typically in commercial system, this area is around 40. So if this pressure is 100 bar, the water which comes out of this would be 4000 bar. That is the basic technology by which we generate such a high pressure. There are different variants of this technology. This is called a single acting intensifier. We have double acting intensifier as well. So, from the intensifier, where does it go? It goes to my accumulator. From the accumulator, it goes to point A, which is entry to my cutting head. Where is my cutting head? This is my cutting head, which is also called the jet former. Jet former. We have already identified or discussed it, but pretty hurriedly. So, here I have high pressure water. Where from it has come? It has come from the intensifier via accumulator. So, water is available here at 4000 bar. What is this? This is my orifice. How the actually the orifice looks like? It looks something like this. So, you have a central hole, a very small hole through which the water comes out, which I have represented here by this one. So, water on this side is issued from the orifice as a jet. Let me clear it once. So, water is issued from the orifice as a abrasive water jet. This water jet velocity would be very high, this much. Now, these abrasives are now being added. They are being added in a chamber which is called mixing chamber. If you remember correctly, this we have already identified under the list of modules. So, what happens? These abrasives are being added at a very low velocity. So, once they are added, they interact with the water, gain momentum and come out of this focusing tube. This is called the jet former. This is the schematic of the jet former, and here you have two typical jet formers which are commercially available. Now, I have described in this what it does, how the mixing process takes place. This is the water jet, this black part of it. So, this is my water jet. Who has produced this water jet? The orifice has issued this water jet. This is coming. This particular part is my mixing chamber. So, abrasives are coming here. This is one abrasive. So, once it is added, it tries to enter the water jet. It cannot enter. Whenever it tries to enter, it comes out. So, the mixing process takes place by a series of interaction with the jet and the mixing chamber and the focusing tube, and gradually this comes out. When at the end of the mixing chamber, the velocity of the abrasive phase and the water phase, they are more or less same. So, it depends on what should be the length of the focusing tube. Typically 75 millimeter to 85 millimeter length of the focusing tube is used. Already I have said this is the inner diameter of the focusing tube, which is 0.8 to 2.4 millimeter. It is chosen depending on what kind of application you are using. So, this slide briefly describes the mixing process. Now, we are going to model the mixing process. This is the process description, but my interest is, can I mathematically model it? Yes, we can do it. What would be my intention? My intention would be, here is my pressure of water Pw. Can I estimate VAWJ, velocity of the abrasive water jet? That is my intention. So, that is called mixing process modeling. The first equation is basically a very simple equation, Bernoulli's equation. Please concentrate here. What does it say? This equation says the pressure head, this pressure head is being converted into VWJ. See, this is not VWJ, this is VAWJ. So, where is this VWJ? Velocity of the water jet which is coming out of the orifice. So, it is here. What it says, the kinetic pressure head is being converted into kinetic head. So, VWJ is root over 2 PW divided by rho W. PW is the pressure of water, rho W as all of you know is the density of water. So, what is this term? This is the velocity coefficient of discharge. All of you must have gone through fluid mechanics, so you know what it is. Now, once I know the velocity of water, later on I will require this equation. So, I have derived them here. What is this? This is the volume flow rate of water. How do I get it? Any volume flow rate through a channel is nothing but the area into velocity. So, VWJ, area of any circular cross section is pi by 4 dO square. So, dO is the orifice diameter. Now, who is this guy? This guy is the coefficient of vena contracta. All of you know, whenever water flows through a particular orifice, there is vena contracta phenomena, there is contraction as it comes out. So, this is that particular coefficient. What is this? This is the estimation of the total power of the water jet, which is pressure into volume flow rate. But our intention was to get VAWJ. How to get that? Already we have done the job, at least to some extent. We have got the velocity of water. Now, after the water comes here, what happens? Abrasive is added here. If you remember, abrasive is added. So, water jet and abrasive interacts, which has already been explained. How do I model it? I model it with a simple assumption. What is that assumption? Assumption is the momentum before mixing and after mixing, momentum here and after mixing remains conserved. So, momentum is conserved. That can be written like this. This is the momentum of water jet before mixing. This is the momentum of abrasive phase before mixing. This is the momentum of air phase, and this part is after mixing, when it is coming out of this particular position. Now, air, the mass flow rate as such is less, so their momentum is almost 0. Momentum is almost 0. Here also the same for air goes 0. When the abrasives are being added, they are being added at a very low velocity. Water jet velocity, if you remember, is 1000 meter per second. This is very, very low. So, this term is also very small. So, neglecting these terms, what we can get the velocity of the abrasive water jet. So, this is my velocity of the abrasive water jet. This term was 0. This is also very small. So, these two terms basically cancels out. So, I have this one, which is this into this, and on the denominator this term becomes 0. So, denominator becomes mass flow rate of water plus mass flow rate of abrasive. By modifying this equation, we get the final expression, which is 1 by 1 plus R into VWJ. Now, all of a sudden I have introduced a term which is R. What is this R? This R is called mixing ratio. What is this mixing ratio? If you study this, this is basically mass flow rate of abrasive divided by mass flow rate of water. It is already here. I have tried to explain there as well. So, this is my mixing ratio. This is an important parameter in water jet machining, abrasive water jet machining. Finally, we have assumed that momentum is conserved, but actually momentum does not get conserved. So, the abrasive water jet velocity as given here, VAWJ, is expressed as eta times 1 by 1 plus R into VWJ. So, what is the difference between this equation and this equation? I am introducing a term eta. This coefficient takes care of loss of momentum. Why the loss of momentum takes place? You have already seen the mixing process is highly a process full of collisions. So, during such collisions there is some loss of momentum. Now, mixing has occurred. This is my jet coming out. It has machined my job. Still there is sufficient energy of the water jet or abrasive water jet. This energy is so much, I can say from my practical experience, it can cut through human flesh. This energy of the abrasive is so much. So, what do you have? This spent abrasives, they need to be restrained somehow, so that they do not damage your workshop, your machine tool, as well as most importantly your man. So, we have a module called catcher, which basically restrains that abrasive water jet velocity. We have water basin catcher. It is the simplest of all. You put a tank in that tank put lot of water. So, the abrasive water jet interacts with that water and loses its energy, but the water tank is a very bulky thing. You can have a small pitcher kind of thing, in that you can have steel, tungsten carbide or ceramics balls. Why? Because these are wear resistant balls, they can interact with this ball and lose their unutilized energy. Or you can have plates, so that it interacts with the plate and in the process loses its energy. But all these plates, these balls should be wear resistant. So, titanium diboride plates are used, ceramics or steel balls are used, or else water basin is used for restraining the spent energy of the abrasive water jet, and this is called a catcher. Now, before going into the mechanism of material removal, let us come back to another kind of abrasive water jet, which is suspension jet. There are three different variants. One is indirect pumping, one is bypass principle or bypass pumping, another is direct pumping. As I said, suspension jet is commercially not that popular as the entrant jet, entrant abrasive water jet, which we were discussing thus far. Here in suspension jet, typically the water pressure is not that high, it is around 500 bar to 1000 bar. In indirect pumping, you have a slurry, premixed slurry, where the water is directly pumped using an isolator. So, the abrasive water jet comes out here. In bypass pumping, you have a premixed slurry, the water comes here through the bypass valve, as well as it get mixed up and then it comes out through the orifice. As because the orifice is handling both water and abrasive phase, the wear strength of this orifice are to be very high. They are to be made of ceramic. Having tungsten carbide orifice is not sufficient. In abrasive water jet machining, orifice does not handle abrasive entrant system, it only handles water. Still we use sapphire orifice. As I said, this suspension system is not very popular because it has been introduced much late as compared to entrant system. Now, before going into the mechanism of material removal, one very important thing is the product quality. So, let us concentrate on product quality. Whenever we manufacture to get a particular product which would be a useful thing to the society. Now, this is the photographic view of the curve. What is the curve? Say for example, this is the curve that I have machined. My jet was here and is being given a velocity like this. So, this is the front view of the curve, and this view is the longitudinal view. So, as if I have cut it with a plane like this. Okay. So, these are the two views. This is my front view and this is my longitudinal view. So, what we can see in the front view? The first thing that we can observe is that I intended to cut it normally, but it has cut in a taper. So, I need to characterize this taper. This is an important deviation. If I do not know how much is the taper, I cannot control my quality. Another very important thing in my longitudinal section is that this is my cutting head, this is my traverse velocity which is being given to the cutting head. The water jet is coming out in this direction. Okay. So, this is the schematic and this is my longitudinal section. What can you see in the longitudinal section? In the longitudinal section, the upper part, this part is rather smooth, the surface is very good, but the lower part you have lot of marks. Can you see them? And they are periodic. So, the mechanism of material removal would be different. Now, if you require the surface to have a smoothness, then you have to set your parameters accordingly. Now, this upper part is called micromachine zone and the lower part is called plastically deformed zone, this particular one. And you can see these marks, these are called striation marks. So, what is the important conclusion of this slide? You have taper, you have smooth micromachine zone, you have plastically deformed zone having striation mark. Depending on what is your requirement, you have to set your parameters accordingly. Now, this is a schematic of the front view. Not only you have taper as it is seen here, you also have two more things, jet affected zone and bar formation. This bar formation is typically important whenever you are machining ductile materials like titanium alloys, steel, something like that. If you are machining glass, it would not be there. If you are machining cast iron, it would not be there. These bars are typically formed because of plastic deformation. Now, this particular slide also show one more thing. What does it show? It shows the top width of the curve and the bottom width of the curve, and they are different and they needs to be characterized in abrasive water jet machining process. Now, we are coming to the front view of the curve. This you have already seen. Here also, depending on what was the process parameter setting, the tapers are different. If you look closely, this taper and this taper, they are different. What could be your conclusion? Your conclusion would be possibly the jet while machining this was not that energetic. Energy part of the it, its cutting ability was low, so it has given you more taper. Moreover, another important thing to see, you have bars. So, when you are cutting with a machining with a abrasive water jet having less energy, it will form bars. Here the bar formation is less. Now, you can also see a cut from the back side. Let us see how does it look like. So, what is this? This was my jet, it was cutting in this direction, I am looking from the bottom. So, view from the back. What is there? Here again the back side looks different. Here it is very good. Here there is to some extent bar formation is there. Here not only there is bar formation, there is another important thing. What is it? See, there is variation. So much of variation in the definition of the geometry. So, once again, what could be the reason? The energy content or the cutting ability was low in this one and was definitely much better in this. But these are issues which are to be kept in mind. If you are using abrasive water jet for something called rapid tooling, then you should not have such bars. Rapid tooling would definitely be covered in some other in rapid prototyping if you have a subject like that. Now, let us come to mechanism of material removal. All the time we are saying it is getting removed. Why it is getting removed? Because of erosion. Basically, there are three distinct mechanism of material removal. One is low angle impact by abrasive grids. This causes ploughing and microcutting, very similar to grinding phenomena, but grinding with loose abrasives. This has been studied by Finney. He is a person from UK. He has studied it long back and it has been adopted by Hashish within abrasive water jet phenomena. There is plastic deformation. Already I have shown you at the bottom of the curve you have plastically deformed zone rather than machined. That has been studied by Beater. Then if you are machining glass or ceramics, not only they would be micro cutting would be there or plastic deformation would be there, there could also be crack propagation, which has been studied mainly by Kim. So, if you are interested in doing your research, you can refer to the work of these guys for a better understanding. However, these models are very sensitive to the choice of parameters. So, they are very involved model, their base is in science, but to the shop floor guy you require a much more easier model which we will come into. Now, this few slide shows what is the evidence of microcutting. Can you see? This is the top of the curve. Here you have a microcutting in this direction. What is the angle? Angle is possibly 25 degree. As you go to the middle, the jet loses its energy, the angle is much higher, possibly around 65 degree. At the bottom, abrasives are flowing like this. So, the angle is almost 90 degree. So, as the abrasive jet penetrates, it changes its local impact angle as it loses its energy. But there is clear evidence, at least in this particular slide, that there is microcutting, there is ploughing, that is side deformation, and in the next slide I can give you the evidence of cracks. This is a special material, I will not identify this material for some reason. This is a special material which has undergone cracks. Can you see that? This is a brittle material. It is a complex material which has undergone cracks because it is brittle. So, we have got evidence of microcutting, we have got evidence of plastic deformation, and for brittle materials we have also got evidence of cracks. You have cracks here, you have got fracture here. So, all this occurs in case of brittle materials. Now, let us come to a model which is rather simple. It is not so involved as proposed by Finney or as proposed by Beater and others. This model has been developed by TU Delft. What is the model? The model is very simple. They try to estimate how much is the power of the abrasive water jet. Once they estimate that, they divide that by the resistance of the material. If these two quantities are known, you can find out what is your material removal rate or what is your depth of penetration. So, what does it say? This is my power of abrasive jet, AWJ. The first assumption, the power of abrasive water jet is equal to the power of abrasive. Water phase does not contribute towards any cutting when you are cutting materials like steel, concrete, metallic alloys, ceramics. If you are cutting leather, that is a different thing, but we are trying to develop depth of cut model for abrasive water jet. So, these two things are same. The abrasive water jet power is equal to the abrasive power. Water phase does not contribute. What is that? That is nothing but the kinetic energy of the abrasive water jet, half mv square. So, this is nothing but half m dot ABR into V AWJ. Already we have derived the equation for this one. Ultimately, we will come to this particular equation, but we are deriving it one by one. Now, mass flow rate of abrasive. Earlier I have introduced a term called mixing ratio. What was that? That was m dot ABR divided by m dot W, ratio of mass flow rate of abrasive to mass flow rate of water. So, if this is R, how much is this? This is nothing but R into this. That is what I have written here. So, this half stays there, half R into this, R comes here. What is mass flow rate of water? Mass flow rate of water is density into its volume flow rate. You can already see this is my area of the orifice, this is my velocity of the water jet, and what is this? This is the coefficient of discharge of that particular nozzle. So, this gives my half m dot ABR, this part of it. VAWJ, already we have derived this equation. So, this is nothing but eta by 1 plus R into VWJ square. This was in a different form, but this is a very small derivation which you can always incorporate. So, at this stage I can derive what is this. Let us go further. Now, what I am doing is that I am basically assembling these two velocities. So, the velocity power becomes 3, area of the orifice stays here, CD stays here, rho of the water stays here, and this eta by 1 plus R I have taken it outside, and by doing a very simple simplification you can arrive at this particular equation. What does it say? It says power of abrasive water jet is related to power of water, basically it is related with a power of 3 by 2. It is also related to the orifice diameter with a power of 2. It is inversely related to rho W with a power of half. It is also related in a complex manner with the mixing ratio. So, with this equation I can estimate how much is my power of abrasive water jet. Now, I need to bring in the resistance part that is offered by the material, that comes in the next slide. So, what I am trying to predict is this one, this is my depth. Why do I need to predict it? Because for a given set of parameters, if I can predict it, I can easily machine it, or else I do not know what should be my parameter setting. So, this is very, very important. So, what do I have here? This particular equation basically tells you what is the energy density. Okay, it is nothing but power of the jet divided by how much area you are generating. This is the width of the curve, which is the insert diameter or the nozzle diameter, which was identified earlier as around 0.8 to 2.4 millimeter, is it not? So, this di, how fast I am machining it? I am machining it at a rate of Vf, thus I am generating an area which is Vf by di. So, this one is nothing but the how much is my energy density. Now, next step says how much is my material removal rate, how fast I am machining. How do I get it? I simply divide the power of the abrasive water jet by the resistance of the material. What is this U job? U job is the specific energy of the material. Generally, it has been seen for metallic alloys like aluminum, steel, it is somehow empirically related to our Young's modulus. Typically, it is E by 14, provided you specify it in appropriate units. So, this is what is the cutting ability and what is how much the energy I require. So, if I take the ratio, what do I get? I get the material removal rate. Once I expand it, it takes a form like this. Now, if you look closely, I have introduced a term Z. Why have I introduced the term zeta? I will come to that after some time. So, after material removal rate, from material removal rate, now I am trying to get HT. How much is my HT? This is my HT. What is my width? W or DI. How fast am I cutting? VF. So, how much is my material removal rate? HT, this much, into DI into VF. That is what is written here, HT into W or DI into VF. Now, W is replaced by DI. So, simply we get a final equation which is like this. Now, whenever we machine, whenever we manufacture, what would be our intention? Our intention would be how fast can I machine, to what extent can I machine, is it not? And moreover, my product quality should be as good as possible. So, our next intention, at least one of them, how to maximize depth of cut. Any practicing engineer, any manager would be interested in machining as fast as is possible, because it is quite often directly related to your productivity. So, what is my objective? My objective is to maximize my depth. How can I do it? This is my equation. Once again, this is my equation. So, you need to concentrate here. So, first what it says, increase water pressure. Does it say the same in the equation? Yes. Look here, your HT is related to water pressure. If you increase water pressure, your depth of penetration is going to increase. Higher orifice diameter, DO. Orifice diameter, as I said, is 0.1 to 0.3 millimeter. So, try to use as large as possible, but there is an implication of using higher orifice diameter. As you increase the orifice diameter, it also affects the mass flow rate of water, which indirectly affects R. Smaller nozzle of diameter. What is smaller nozzle of diameter? This is, if this DI is less, definitely your material removal would be much higher, your HT would be much higher, because this is in the denominator. So, it is the same thing, smaller nozzle diameter. So, DI is in the denominator. Lower traverse speed, definitely if you machine at a less speed, you will be able to machine, you will be able to penetrate more. This is my nature of the curve. Then sharper grids. I have never talked about what is the shape of the grid. Definitely you can understand, if you take a blunt knife, you will not be able to cut a vegetable. If your knife is sharp, it would be able to cut it much easily, your effort required would be less. Similarly, a grit can be totally spherical, or it can have irregular shape, or it can be sharp. This zeta basically incorporates that sharpness of the grit. Efficient orifice and mixing chamber. We have talked about quite a few coefficients. One is this, phi, psi, eta and zeta. This is talks about the material sharpness. What are these? This is the velocity coefficient, this is the contractor, CD was there, which was discharge coefficient. If your orifice and nozzles are efficient, then these values would be very near to 1. So, that is also required. Bigger grid diameter. Bigger grid diameter is not reflected here, however, it has been seen for the same energy level, if your grid's diameter is higher, then also this tends to be higher and you get a higher penetration. Another very interesting thing, what should be my mixing ratio R1? Generally it is never said go on increasing ABR, mass flow rate of abrasives. No, if you differentiate this equation with respect to R, you will see at a value of mixing ratio of 1, the maximum cutting ability is achieved. However, this is theoretical model. Practically it has been seen, it is not an 1, this is theory. Practically somewhere around 0.7 value of R this occurs. Now, let us come to the limitations. I would not say the limitations, but environmental issues of abrasive water jet machining. You are using water, so you need to recycle them. We should not use any manufacturing process which ultimately pollutes our environment, because we need to preserve our environment not only for us, but for our future generation. We should not dispose the water here and there. So, this also includes economic cost. Cheap recovery is an issue. Whenever we are machining cheap and water, they are getting mixed up. We should not throw them and pollute the environment. Still, I would say abrasive water jet machining is rather a friendly process or environmentally benign process. But there is also the issue of abrasive recovery and reuse. It helps us in reducing the cost as well. Now, this is the future of abrasive water jet machining. This is not called abrasive water jet, rather abrasive cryogenic jet. Instead of water, liquid nitrogen is used. Instead of abrasive, dry ice or carbon dioxide is used. You do not have any waste after you have machined. Absolutely no waste is there. So, possibly this is the future where abrasive water jet is gradually moving towards. The water is replaced by liquid nitrogen and the abrasives are that of a dry ice. Now, let us come to the summary part of it. What we have learned today? We have learned about abrasive water jet machine as well as water jet systems, different modules of abrasive water jet systems, applications and advantages of application water jet systems, their materials, functions of different modules, not only identify modules, but their functions, modeling of mechanism of material removal. This is very important, because once you have the model, you can try out that model to set parameters. We also know the product quality issue, taper is there, bar formation is there. If you remember, the limitations of abrasive, as such there is no limitation, but there are some environmental issues which are to be looked into and future direction in the area of abrasive water jet. Before I end, I mentioned that after this you have 4 solved problems and you have 4 quiz questions. Please go through them, and if there is any queries, in the very first slide the email address is given, you can always come back to me. Thank you. With that, I end my lecture today.